All right, welcome to the video on 7.4, medians. Medians and something called the centroid. So first off, we gotta know what medians are. A median of a triangle connects a vertex to the midpoint of the opposite side. So this would be a median. Here's a vertex, here's the midpoint of the opposite side. That is a median. Triangles would naturally have three medians because they've got three sides. So they got three spots where it could go. I could connect to, it's rough, that midpoint looks roughly there. That would be a second median. And that looks roughly there for the midpoint of the last one. That'd be the third median. And as you notice, the medians appear to all intersect in the same point as well. That is the third center of a triangle we're going to learn, and it's this, my favorite. It's called the centroid. So I'm going to show you a construction of the centroid, and I'm going to explain why it is my favorite. Okay, so here I made a triangle. I constructed the medians of the triangle. Here's a median, here's a median, here's a median. You might recognize these construction marks here as a construction marks for a perpendicular bisector. Yes, I use those to construct my median, but make sure you are not actually constructing perpendicular bisectors. Perpendicular bisectors would have connected these 2 points, and it would have been perpendicular, which you'll notice is not the same as that median. Perpendicular bisectors would find the circumcenter. I used the perpendicular bisector construction not so that I could find the perpendicular bisector, but so that I could use those points to find the bisector, the midpoint. So I found the midpoint of the line by using that perpendicular bisector construction. Once I found the midpoint, I could connect the midpoint to a vertex, so I could find the median. So here are the three medians, and they all intersect in the same point. And why that point is called the centroid. And why that center is my favorite is because that centroid is actually the center of gravity of a triangle. If you had a uniform triangle, a triangle of uniform thickness, and you cut that triangle out and you found a centroid, that centroid is the exact point where the triangle would be balanced if you put it on some sort of point. I'm going to actually try to cut this triangle out and balance it to demonstrate how that centroid is the balancing point. All right, so here's my triangle where I found the centroid. If you wanted to try this at home, it's kind of fun. I would recommend thicker paper. The thicker paper, the better, because it'll help any breezes would have less effect on tipping it. Also, I would recommend a nice, I'm going to use a pencil with a flat top, because that's going to give me a little bit more room for error to make sure I get there exactly. There it is. Balancing point. All right, so we learned that the centroid is the intersection of the medians of a triangle. Medians, again, connecting the vertices to the midpoints. And it is the center of balance for a triangle, or the balancing point. It's the center of gravity. So there is a picture of it, the centroid, all the medians, and that's a balancing point of the triangle. But that's not all about medians. There's more things about medians that are kind of interesting. Note, the medians of a triangle divide a triangle into smaller triangles of equal area. So one of the things, because it's a balancing point, all of these different triangles here are going to have the same area. If they had a different amount of area, they'd have different mass, which means one side would be heavier than the others and it wouldn't balance. So all of those have equal area. But you will notice that they are not all the same shape, right? So even though they have equal area, they are not the same shape. So different shaped triangles, but all having the same area. I'll leave it to you to read the proof. It's in your book, kind of a cool little proof. One other thing about medians and the centroid will cut medians in a 2-to-1 ratio. So wherever your centroid is, you'll notice the medians will all be cut into a long segment and a short segment. And that long segment will always be twice the length of the short segment. So all three of these medians are being cut in a 2-to-1 ratio. Again, their lengths aren't necessarily the same length, like B and A aren't necessarily the same length, but whatever B is, this long part of it be twice that, 2b. All right, some practice problems. Here we're given that MP and LN are medians, which means they are connecting midpoints. And it's giving me that triangle LCP, this triangle here, has an area of 6. So then it's asking me, what is the area of MOP? MOP, that one right there. All right, well, I know that the 3 medians would all cut the triangle into equal length, equal area triangles. So if I had all those medians in, I know this triangle here would have an area of 6, and this triangle here would have an area of 6, and this triangle here would have an area of 6, which means triangle MOP must have an area of 18 square centimeters. Again, because the medians cut the triangle into 6 different triangles, all with equal area. This one had an area of 6, so then all the other triangles in there, all 5 others, will have an area of 6. All right, another example problem. I'm being asked to find the lengths of JM, JO, and OM, all 3 of those ones there. And they gave us some information. I was given that this one here is 10, that whole one there is 10, and this big long one here is 16. I was also given that these are medians, which means that this is cut in half. And if I wanted to look at just that right-hand triangle, since this whole length is 16, just this part of it would be 8. And just this, no, on that whole part would be 6. Sorry, that was given to be 10, right? JL is 10. And I've got that triangle there. It would be really tempting to say it's a 6, 8, 10 triangle, right? It's a right triangle and find out that whole length is 6, but I don't know that for sure yet. All I know is that this one's 10, that one's 8. On the other side, again, since this whole thing was 16 and that was a midpoint, M was a midpoint, this would be 8. And this one, oh, KJ, that was given to be, JK was 10. Ah, here we go. Take a look at that big triangle. KJL. KJL is an isosceles triangle. If it's an isosceles triangle, we know, hold on. We know that the base angles are congruent. So that angle and that angle are congruent, which means this triangle in red is congruent to the triangle that I highlighted in black. Let's pick a different color than black. Let's highlight it in maybe blue, light blue. There we go. I know those 2 triangles are congruent from side, angle, side. And if they're congruent, all their angles are congruent, which means these 2 angles are congruent. And since they form a line and they're congruent, each one must be 90. Ah, that is indeed a right triangle. Since it's a right triangle, I know that JM must be 6, because that would be a 6, 8, 10 triangle. You could use a Pythagorean theorem. Right? A squared plus B squared equals C squared. Since I know JM, I can find JO and OM because they split in a 2-to-1 ratio. So let's call this one, let's call OM X, which means JO would be 2X. And I know if I take JO and I add OM, that's the length of JM. Well, I called OM X. JO would be the longer one, that'd be 2X. JM I found was 6. So 3X equals 6, so X equals 2, which means OM must be 2. Right, because OM was equal to X, and JO, which was equal to 2X, must be 4. There it is. All right. One last video would be a video on altitudes and something called the orthocenter. See you then.